Wait. Very sorry. I have no idea. She was like grade 3. I know the we got photos wrong. It was well, I'm gonna do it in pencil. Remember that? That was goodbye. Remember that when you looked like that? You did something that.
Okay, so from your homework, you guys were asked to find the derivative using implicit, both first and second derivative. So we didn't really get a chance to go over second derivative, even though it was part of your homework. So why don't we back up and do some of these problems together so that you can see what a second derivative can feel like for when there's implicit involved. So let's do 47 from scratch. Our goal is to find y prime and y double prime for x squared plus y squared equals 4. So if I want to find y prime, in other words, I want to find dy dx, that's y prime, and then y double prime can also be represented using this notation d2y over dx2. This is just a notation to indicate that you're asked to find the second derivative. It doesn't mean that you're squaring. Some students interpret this as squaring the first derivative. That's not the case. That's just a notation for second derivative. So we're going to find dy dx, which is y prime. So we see that there's a need for implicit because there's y mixed into our equation. So as we find our derivative, our dy dx will pop up when we ask for y's derivative. So our derivative becomes 2x plus 2y times what? dy dx equals, get 0, right? 4 is also getting impacted by our derivative process, ends up giving us 0. Okay, so now we're going to get dy dx by itself. Before, if it was a function, your dy dx would just automatically be by itself, but now with implicit, with your with the y variable mixed into the equation, our derivative is going to be also mixed into our equation. Divide both sides by 2y. Which is negative x over y. Okay, so are we good with the first half of this problem, finding dy dx? So I'm going to box that off because that is now going to be our starting point for our second part. So imagine if this was the starting point and you want to find the derivative again, which will take us from first to second derivative. So what process do you think we have to involve if we want to find the derivative again? Good. Quotients. And again, we have to involve what? Implicit, yeah. Again, y is mixed into our equation, so let's step through quotients. I'm going to call this f. I want to find the second derivative, so this is now going to turn into d2y over dx2. I'm going to set up my quotient rule here. Again, you guys don't have to do all this, writing all this out. I'm just doing it to help us see, just for demonstration purposes, so you can see exactly why the pieces are going where they are. All right, what's f prime going to be? -1. G function, no changes. Back to f. What's g prime going to be? Right, 1 dy dx. You can drop the 1 if you wanted to, but yeah, definitely need that dy dx. All over y squared. Any questions? So we found the second derivative. We're done with the calculus. Now we just want to be able to clean up the derivative down to as simple as possible. Okay. But no questions so far. Okay. So now the next thing is we would like to represent our second derivative just in terms of x's and y's. So we would like to find a replacement for this dy dx. What do you think I can replace dy dx with? Negative x over y. Okay. So everybody good so far still? All right, I want us to see if we can get this cleaned up even further. So there's a complex fraction in the numerator. We're going to find common denominator, try to compress with or condense with that denominator, see if we can collapse with that denominator. So I'm going to write this as negative y over 1 minus x squared over y all over 1 squared. Now, we know the numerator can clean up or can merge once we get common denominators. So I'm going to get common denominator as y. Balance each of the fractions. This one is missing a y, so multiply top by y as well. This second fraction, no changes, so I'm going to leave it as x squared over y. Sorry, y squared. Okay. Now this can merge into one fraction up at the top here. So I get negative x squared minus y squared over y all over y squared. Okay. No calculus, right? We're just trying to do all sorts of cleanup. Now, dividing by y squared is the same thing as multiplying by the reciprocal, right? 1 over y squared. So we reset here. I can multiply the y with the y squared. Any questions? Yeah.
Yeah, that's good. Negative y squared over 1 minus x over 1 is negative x squared minus y squared over y as opposed to negative y squared minus x squared.
Oh, you mean from here to here?
Yeah.
Yeah, I accidentally changed the order, but it doesn't really matter. They're both negative, so it could be negative y squared minus x. Yeah. So this is an acceptable answer because we got everything down in terms of x and y, but we can actually go further. We can actually make another set of substitution, and it has to do with the original equation. You see another thing that we can substitute to make this look even? I could factor a negative 1 out. And I can replace this x squared plus y squared with what? 4. So if you're asking, do I have to get to this point? Yes and no. So if it was free response, you could potentially leave your answer in this form and be okay. But the reason I wanted to show you to this point is because if this was an AP exam question, they may clean it all the way up to this stage. And if you're stuck at your version and not knowing how to get to that version, it's usually because they're using a substitution from the original equation somehow. Any questions with the process? So before we move on, let's see. Can we try one problem on our that's not part of our homework, but is similar to this one? Let's do 48 and see if this makes sense. Can we go through the process of first derivative, dy dx showing up, and then second derivative, making that substitution for that dy dx again. So I'll write 48 here, and then have you guys try it, see if that process makes sense. Okay. X squared minus y squared equals 1. But I'll leave 47 up so you can kind of, it's going to feel very similar in terms of the steps. Everybody got this down? X squared minus y squared equals 1. Okay, try that, but I'll leave 47 up here so you can use this as a way to match your work. And I'll work out 48 as well, and we'll go over it. Go ahead. At our halfway point, our derivative should be x over y. Let me go through quotient rule again. Sorry, we go through quotient rule for our second derivative. right? Quotient rule to get to the second derivative. Once you get your dy dx to pop up, replace that dy dx with x over y from your original first derivative. And then once everything starts with x and y, we got to resolve that complex fraction, common denominator, to merge the two fractions together, and then multiply by the conjugate. Sorry, the conjugate, the reciprocal. And then we look for the chance to make another set of substitution from the original equation. We get all the way down to -1 over y cubed. Any questions here? Or before lunch? All right, so your homework, it will have more implicit differentiation for you to practice with. And I'll send out a reminder about your homework Wednesday. But Thursday morning, if you have any questions about your homework, I'll also be available for a help session if you need additional help with implicit or today's topic. So today we're talking about the derivative of the inverse at a point. So let's go to page 23. All right, so today's topic is derivative of an inverse at a point. We know an inverse function is found by swapping the input x and output y values. So your domain and range are also going to be swapped between the function and its inverse. So just to kind of have a little bit of background and review, if I want to find the inverse function of y equals 6x plus 2, there's two things I need to do, right? I need to swap the x and y, and I'm going to solve for my new y variable. So if I swap the x and y, I'll get x is equal to 6y plus 2. If I solve for my new y variable, subtract 2 from both sides and then divide by 6. So the notation to indicate that this is the inverse function, we say f inverse of x is equal to x minus 2 over 6. So one of the properties of inverse function is if I were to insert the inverse function into the x of the original function, everything will cancel out except for the x. Likewise, if I were to insert the function into the inverse x, everything will cancel out except for the x. Okay. Here's a visual representation of what an inverse function, a function and its inverse can look like. They're always going to be folded along the line y equals x. So if I were to fold the graph along this dotted line, the two graphs will overlap each other. So if I wanted to find the inverse function from the function, I can just take this, fold it over, and then that whatever shows up is my inverse function. And so the fact that everything cancels out except x also makes sense because exactly what's between the two graphs is this line y equals x. All right, so let's say we had an order pair on the function, and that order pair is 2, 1. Sorry, 1, 2. Now, if inverse is truly the inverse function, that means there must be an order pair of what that lives on the inverse function. 2, 1, yeah. So all your order pairs are flip-flops, right? This is not the equations of this graph, but it's the same process, right? If we're swapping every x and y with each other, then it makes sense that every order pair is going to have a flipped order as well. So there's an order pair that here is 2, 1. So it also makes sense that all your domains will be flip-flopped, your ranges will be flip-flopped. The range of one is domain of the other. The domain of one is the range of the other. Okay. So we know this is to be true, right? We know that every single order pair, I can flip it, and that new order pair is going to show up on the inverse and vice versa, right? But what we're really talking about today is that at these points, I call them corresponding points because they're related to one another in the sense that they're just flipped orders of each other. There's also going to be a slope that's related as well. And let's say that this function has a steepness of 3 at this point. F prime of 1 is equal to 3. There's a numerical relationship with the inverse. So I'm going to write it as well. This is the derivative of F inverse at 2. Notice that I say 2 because it's at a different point. If you had to guess based off of this, and you know that there's a numeric relationship, if the slope of this is 3, what do you think the slope of this would be? 1/3, yeah. And so that's really what we're doing today. We're just understanding that at these corresponding points, the steepness at their points will be numerically related to each other, and it's simply the reciprocal. Okay. Notice that they're both positive slopes. It's just that one is steeper than the other. So this is really what we're learning today, and we're just practicing understanding where we are on our graph and being able to get there. Any questions? Now, this is what I like to do. This is my preference because the formula just feels like there's a lot of things going on. And I like to organize what I'm gathering in this little chart. So whatever I'm looking for, I'm always going to be putting it down here in the bottom corner. And but I have the first row showing the relationship between the order pairs between a function and its inverse. So if there's an order pair that is a comma b on the inverse, there must be an order pair that is what? B comma a. Yep. So this is how the problem is going to be. You're going to be asked about the derivative of an inverse at a point, but you're going to be given information on the function side. So we're going to have to kind of collect information kind of backwards here. So the idea is that if I can figure out what my order pair is on the function side and then find the derivative at that point, so I can go through my process of power rule or quotient or chain, whatever is needed on the function side, find the slope. Let's say the slope is n, some slope value. Then I just have to take that number and then flip it and represent that as the answer. So even though you're going to be asked about the derivative of an inverse on the inverse function, you're going to be working on the function side because the function side is easier to manage. Find the slope of the derivative on the function side, and then knowing that slope is related to the slope of the corresponding point, and just take that slope and flip it. So we're going to be working on the function side, even though we're asked about the inverse derivative. This is technically the formula, but I just find it to be harder to interpret, but I'll just go ahead and write it out. But I'm going to teach it this way. I feel like if we can just kind of move our way through this chart, eventually we're going to gather enough information to get our answer. Okay. So here's example B. We have our function x cubed plus 4x plus 2. It's some cubic function. We're trying to find the slope of the inverse at -3. We don't have the inverse function. We have the function in front of us. We're not going to go and try to find the inverse function. It's going to be too complicated. We're just going to rely on the function. So I'm going to create a chart, and we're just going to work our way around this chart. At the bottom corner, I'm going to put what I'm looking for. And I'm just going to work my way around this chart until I've gathered enough information. Once I gather enough information, I'm going to know what the slope is. So this is how I want us to fill out the chart. Now, this is the x value of my inverse function, right? So I'm going to put my inverse function above. This is the derivative side. This is just the order pair side. Now, this is asking for the slope. I'm looking for the, -3. I miscopied. We know -3 is the x value of my inverse, but right now, do I know the y value of my inverse? Not yet, right? But I'm going to go to the function side, and I'm going to create that relationship. If -3 is the x value of my inverse, then -3 must be the what of my function? Y value. So I'm going to put that as my y value. Are we good with getting to that point, right? So without even looking at my function or at my problem, as long as I know that's the x value of my inverse, x value of my inverse, y value of my function. Now, this is how we're going to move on. We have our function in front of us, so we can actually use this to help us find the x value of my function. What can I do with this -3? Set equal to the function. Okay, so I'm going to step to the side here and say -3 is equal to x cubed plus 4x plus 2. And we're going to work backwards to figure out what the x value of my original function is. This is tough to solve in terms of algebraic, in terms of factoring, but I'm going to bring everything over to one side, get a 0 to show up at least. X cubed plus 4x plus 5. Now, if you see a problem like this where you can't factor and you don't have a calculator in front of you, you're just going to go through a series of guess and checks. You're going to figure out what x value will allow this equation to be true. So that feels daunting, but if you see a problem like this, it'll be an easy number. It'll be a number, integer number close to 0. So if 0 doesn't work, then try 1. If 1 doesn't work, then try -1. And usually after a couple of tries, you're going to be able to get it. It'll be probably ranging between -3 and 3. Right. So 0 doesn't work, right? If I plug 0, I get 5 equals 0. That's not true. If I plug 1, it doesn't work, because then I get 10 equals 0. What about -1? -1 works. So I get -1 minus 4 is -4, -4, -4 minus 1 is -5, -5 plus 5 is 0. So I guess and check my way through. I couldn't factor. I don't have a calculator. So, but it's an easy number for me to find. So now I know my order pair. I know the order pair that we're dealing with on the function side is -1, -3. And on the inverse side, what's my order pair? -3, -1. Okay, so this should always be here for us to see that, okay, these are inverses of each other, my function and inverse, they must have flipped order pairs. But again, we're not going to do much on the inverse side. We have the function in front of us. We're going to use the function to help us get to the slope that we want to get to. So our goal is to find f prime of -1. So if I want to find f prime of -1, I first have to find what? F prime of x. So f prime of x is what? 3x squared plus 4. Okay, now I can find the slope at that point. What's the slope at that point? Plug 1 in, I get what? 7. So the slope of my function's derivative is 7, which means that the slope of the inverse, which we're not even touching, but we know there must be a clean relationship. The slope of the inverse at its corresponding point must be what? 1/7. Just 1/7. Yeah, I know that you may want to say -1/7 because you're thinking perpendicular lines, opposite reciprocal, but it's just a reciprocal. If you look over here, right, the steepness, they're both positive slopes, so the sign is not going to change. There's just going to be reciprocals of each other. Okay, any questions? When you get to this step here, sometimes you're able to solve algebraically, but if you can't solve algebraically, then you're going to do guess and check, and guess and check, you're just going to test easy numbers. It'll be an easy number for you to find. Okay, so let's try example C. And let's go through this process. So basically, I'm always starting at the bottom corner, and I'm working my way around this chart. And by the time I get to here, I have enough information. By the time I come around full circle, I have the value that I want. So I'm looking for the slope of the inverse at 1, but whatever is given to you is always on the function side. You're never going to be given the inverse function, and you're not going to try to find the inverse function. You're going to do everything on the function side, get the data you want, and then adjust it to the slope that must be, that's the proper relationship. So I'm going to just fill out what I know. I know that 1 is the x value of my inverse function, and therefore 1 must be the what of my function? The y value. Yep, y value. So now I'm going to go to my function and see if I can figure out what the x is at that point. So plug 1 in for y, and I think this we can solve by hand. Right? Square both sides, add 7. X must be equal to what? 2. Okay. So I'm going to fill out my chart here. I really don't have to fill this one out, but it's just nice for us to visually see, okay, my order pairs are flip-flop. I should be able to see that relationship. So now, if I can find f prime of 2, then I'm basically at near the end of my problem. So to find f prime of 2, I first have to find f prime of x. To find f prime of x, what process do I have to go through here? Chain rule, yeah, but let's first rewrite it. Parentheses is my outside function. The x cubed minus 7 is my inside function. Outside's derivative, 1/2, parentheses, so -1/2. We keep the inside intact, times the inside's derivative. X cubed minus 7 becomes 3x squared. Maybe I can do a little bit of cleanup before I plug in 2. It's up to you. All right, this cleans up to be a slope of what? 6. So if the slope of my function produces 6, that means the slope of the inverse at its corresponding point must produce a slope of what? 1/6. That's our answer. The most common mistake that I see is just um, students getting mixed up with the x and y values. They see that one and they instinctively want to plug the one into the x of the function, but then that just goes down the wrong path, right? So just keep reminding yourself the number that they give you is the x value of the inverse, but it's the y value of the function. So we just have to make sure that we are always replacing the y of the function with one with the number that they give you and not putting that as in the x slot for the function. Okay, next page. Sometimes you're given information from a table's perspective. So, but I still like to use the chart to kind of gather my information and just work my way around the chart the same way as if I had the function in front of me. So here, this is an indication. If they give this to you, this indication, okay, my g and f are inverses of each other. There's going to be that relationship where the x's and y's are flip-flop, and then the slope is going to be reciprocals. And it says, find what is the value of g prime of 1. So I'm going to just create my chart. I know I'm looking for g prime of 1. So I'm just going to work my way around. And by the time I make my way around, I'll have my answer. Without even looking at anything else, I know that 1 is the x value of my g function, which must mean that 1 is the what of my f function.
Value.
Yeah. So if you can set up to this stage, then that's the hardest part because everything else you can just fill in using the table. But we just have to make sure we understand this 1 doesn't go in the 1 slot. It doesn't go in the x slot. It goes in the y slot. So notice that we don't have anything on the function side. I'm sorry, on the g of x side, but we do have this, right? What can we fill in for this slot? F of what equals 1? 2. Right. F of 2 is equal to 1. We use this chart here to work. So if 2 is the x value of my function of my f of x, then 2 must be the y value of my f of x. Sorry, yeah, y value of my g of x, sorry. So then if I can find f prime of 2, then that number will lead me to g prime of 1 because they're inverses of each other. Okay, what's f prime of 2? -2, right? The table tells us that. So then from here, we can take the reciprocal. Number 2 says write the equation for the line tangent to f inverse. Again, f inverse is g of x. F inverse at x equals 1. So what's my order pair at my inverse function? 1 comma 2, yeah. And then the slope we just found. And then point slope form. Okay, any questions? Okay, so if you know how the chart works and if you know the flow of the chart, then you can just always use it, gather enough information, and just understand that relationship. Okay. So you guys have homework from the rest of implicit differentiation, and also I think a little bit from derivative of inverse at a point. We can do a little bit of review on Thursday before we move on to the next topic. But yeah, clear your calendar. I'll send out a reminder next Wednesday that I'll be checking homework on Thursday. And then I also have a help session Thursday morning if you have any questions, if stuck on your homework. All right, come get your phones. Great, I'll mark it down. Thank you. No problem.
Okay, I was going to.
You literally Wednesday.
That's good. You're good. Thank you.
I did with that effort. Ron showed me. Bacon, so like I don't talking. But I've seen that. Bro, why did you AC Duncan on? Oh yeah, we're leaving here. No, sleeping like 6:30.
So it's just gonna be two more things than that.
Yeah, let me look at the calendar.
It's just this and then like I think log differentiation or no.
I love logarithms. I really don't.
Yeah, law of differentiation. Yeah, and then you're right. That's it. Inverse functions. Oh yeah, so we're a little bit ahead. That's good. So I may try to get ahead doing that so we can have more time, more days of practice before your test. Yeah.
So is the majority of the test is gonna be like the quiz?
Yeah, it's because we need the quiz topic to be able to do a chain rule implicit. So I'll give the quiz back to you Thursday or Friday. You can look over it and do it. But yeah, 3 is basically like the test version. Because in the past, 2 and 3 were combined in the same unit, but now it's different unit. That's why we had a quiz for unit 2 and the test.
Okay. And are the the lectures are on your window? Yeah, because I was just out, so I know like up in the table, but then like yesterday.
Yeah, look over. Work through the notes, see if the video helps. Yeah. You can come in Thursday morning and have questions.
Thank you.
Okay.
Yeah, I'll be on.
Okay, sure.
Chain. Yeah.
You don't think CNC?
I don't.
People are doing like.